Ready to go. So I would like to welcome you to today's webinar provided by the Statistics Division. My name is Stephen Scholka. I am the past chair of the Statistics Division. Our webinar will be recorded and will be available within about a week on the Statistics Division YouTube channel. And also, if you're a member of ASQ, go to our My ASQ page and you can see some of our past webinars and our future webinar. We have one scheduled in early November on chi-square testing. So with that, I'm going to introduce Dr. Stephen Bailey. Steve received his BS, MS, and PhD in statistics, all from the University of Wisconsin, with his thesis done under the supervision of Dr. George Box. He completed a 36-year DuPont career in 2016 with their corporate applied statistics group, retiring as their principal consultant and master black belt. Steve has been an ASQ member for 35 years, leader for 35 years, most notably as the president in 1997 through 98, and the chairman of the board in 98 through 99. Steve is an ASQ fellow and recipient of ASQ's Distinguished Service Medal. Steve is a certified black belt and a master black belt by both DuPont and ASQ. And with that, I'm going to let Steve have at it. All attendees except myself and Steve have been muted. If you have questions, please submit them in the chat box. And when Steve is done, I'll be able to share those with Steve for hopefully an intelligent and delightful answer. So with that, Dr. Bailey, have at it.
Thank you, Steve. My talk today is George Box, DuPont, and Successful Experimentation. And let me begin with George. This Friday would have been George's 100th birthday. George passed away in 2013. They're actually going to have a celebration this Friday in Madison, Wisconsin at the University of Wisconsin to commemorate his life. And unfortunately, I am unable to make that due to a couple of other commitments, but that made me think this might be a good time to reflect a little bit on what George has contributed and also how it relates to the DuPont part of my talk. And then I'll ultimately get to 4 short case studies of successful experimentation. There's many places to look at the contributions George gave. And one in particular I like, which came out right after he passed in 2013, was in this special issue that a number of folks, most of whom are actually students of George Box, wrote various aspects of his life, talking about what he did in design of experiments, in time series, in Bayesian inference, in process control, and so forth. So that's a good place to look. I've highlighted 2 names in red here, Dave Bacon and Conrad Fung. They, along with myself and a couple of others, are both ex-Box students and ex-DuPonters. So I'll mention those as we go along. Actually, Conrad is on the next chart. I don't expect you to read this chart, but I was looking for a picture of George and myself and maybe some others, and about the best I could come up with, interestingly enough, was right when I joined DuPont in the early 80s. We actually had George come out and we gave DuPont, taped him in the Industrial Statistician series that ASA put together. And we also had Stu Hunter and Bill Hunter there, Box Hunter and Hunter, seminal textbook on experimental design. In the background there in the top left picture is Conrad Fung, and then myself there. At the bottom picture has George and my first supervisor at DuPont, Ron Snee. So just thinking a little bit back at my transition from the 70s in Wisconsin to DuPont in the early 80s. About the best picture I have of George is one. This is like 2 decades ago that he's having a nice little dance with my wife, Mark. And this is right after George was named ASQ's 21st honorary member. So that was kind of a nice little touch. So how does George and DuPont relate? A particular article in Chemical Engineering News was entitled back in 2013, Design of Experiments Makes a Comeback. I don't think it ever had to make a comeback in DuPont. It was kind of like a very highly used tool and strategy in DuPont. But I did kind of chuckle a little bit from this article. It said kind of simplified the design experiment world as 4 milestones. And the first was Ronald A. Fisher, of course, his agricultural experiments. The second, of course, is George Box. And then the third, they mentioned DuPont, where we, would train our internal employees on design of experiments, and in fact offer that training to other companies way back in the 70s, well before many other DOE courses were out there. The last thing they mentioned in the article is the Food and Drug Administration Quality by Design initiative. So any event, so there's George and DuPont somewhat kind of linked. And actually, George was involved early on in the development of our Strategy of Experimentation, or SOE course, which actually was born in 1964, as you can see in red on this chart. This chart really is a poster that I put together in DuPont on the 50th anniversary of Strategy Experimentation. That was 2014, and includes a little bit of a pledge of allegiance to the article. So any event, there's a long history of how the DOE theory in one column over the decades was developed, what areas it was applied to, the various courses we had, and the audience for those courses. And I'll just make a side comment in the middle. We talked about software that went from handheld calculators to UNIVACs to some of the early statistical software packages that address design of experiments to today. The examples you're going to see in the presentation are going to be done with Minitab, but of course they can also be done with JUMP or Design Expert or many other software packages as well. Just make that point here. So in DuPont, the strategy of experimentation basically it was a strategy, and it recognized the evolution of the experimental environment, going from screening out many possible factors that are important to characterizing the effects of a smaller number to an ultimate optimization across those factors to get good products and processes. In the middle of this chart is the basic building block for these good designs, 2-level factorial designs, full factorial designs in the middle there. The screening on the left would be when you can't, for whatever reason, run all of the possible combinations of the factors at 2 levels each. And of course, I can only picture 3 here, and I would hope if you had only 3 factors, you'd actually run the experiment in the middle with all 8 corners rather than just those 4. But the idea is if you had to run just 4 experiments, those would be the 4 to run on the left, or the reverse 4, the other 4 that are not shown, because they have good balance and orthogonality properties, which we'll talk about shortly. So any event, this very powerful strategy experimentation used in DuPont. So with that, let me just talk about the outline for the rest of the webinar. I did talk a bit about George and his 100th birthday and his contributions, talked a bit about our DuPont's strategy experimentation history, now up to 55 years in 2019. I mean, even as I speak, I know one of my other colleagues, Kim Hockman, is delivering a strategy experimentation course in DuPont, so it continues there. Any event, the rest of this presentation will have 2 sections. One is a little bit on screening experiments. I'll give a little bit of background and then 2 examples. And I will follow that with some optimization experiments, a little bit of background, and 2 more examples. The screening examples will use what I'll call classical designs. They're cataloged, they're out there. George pretty famously documented their properties with Stu Hunter and so forth, and we'll talk about those. Optimization, of course, George and his colleagues develop response surface methodology. another set of catalog designs, but we'll talk about the use of custom designs to apply to a couple of examples. So let's start with the screening piece, two-level screening experiments. In green, they're successful because they are balanced and they're orthogonal, and what that means I'll show in the first example, but basically for two-level designs, this means the number of experimental runs is a multiple of 4, and they get run. These experiments actually get done, which makes it very valuable. So what are the technical questions? Or just a couple, really. How many experimental runs should we include in our designed experiment? And what is the effect of ignored second-order effects? These screening designs are trying to look at the main effects to identify the critical few X's or inputs from the many that you're studying in the experiment. But there are second-order effects that may cause us some consternation. Two-factor interactions, where are they in these screening designs? And curvature, how is that addressed or not addressed? Those are second-order effects that is the other technical question. So as I go through the two examples, the first one will be one of a Plackett-Burman design. It'll be a 20-run design. And the second one will be a 2 to the k minus p fractional factorial design, 8 factors k, a 16th fraction of that, so 2 to the 8 minus 4 specifically. We'll see what the benefits are of these and how to resolve the technical questions. The first technical question, however, the idea of how many experiments should we actually run is fairly straightforward, and another colleague of DuPont, Bob Wheeler, who literally left DuPont at his 15-year mark to go and create a software package called eChip for experimental design, which was out there for a long period of time. Bob's passed away, but was one of the early adopters of using software to execute experimental design. He had what's called a portable power rule of thumb, and this is the rule of thumb that says if you want to pick up a delta-sized effect and you're trying to fight through with a sigma-sized noise, the signal-to-noise ratio, delta divided by sigma, you can have a right-sized experiment to pick up a 2 standard deviation size effect in as little as 12 to 16 experiments. You're going to need 49 to 64 experiments for a 1 standard deviation size effect. So that's the sweet spot. I don't think anyone goes all the way to half a standard deviation goal. If they do, they need several hundred experiments to achieve that. In any event, it's a good rule. It's independent of how many factors you have, K. It's the 7 or 8 in the numerator is just a good balance of what the underlying alphas and betas might be for this type of sample size calculation. But it's a quick rule of thumb to remember. So let's talk about the second technical question, that one of where do the second order effects go? And let's talk about the interactions in particular and bring up the concept of resolution. What is the resolution of a design? And the easiest way to describe this is with the grouped finger rule. So if I throw up 3 fingers for a resolution 3 design, I'll take 1 finger and I say that's a main effect. It's confounded with the other 2 fingers, a two-way interaction. Okay, so the effect of factor A is going to be confounded in some way with the interaction of factors B and C, for example. So that's resolution 3. We can get a little bit more resolution if we go to resolution 4. Main effects in that case are just confounded with 3-way interactions, so we get a clear view of the main effects in this type of design. And the 2-way interactions are confounded with each other and put off to the side, so they're not affecting the main effects. That's good. And then ultimately, if we go to resolution 5, we've got main effects are confounded with 4-way interactions, so main effects come out really clear. 2-way interactions are confounded with 3-way interactions, so we tend to treat them as the 2-way interactions, and we can get a full second-order model of main effects and interactions with that. So in Minitab, they kind of use, everyone likes stoplight charts, red, yellow, and green, and so these resolution 3 is red, and yellow is 4, and green is 5 or above. I like to make a little bit more detail of that chart. And I'm going to borrow Tom Ridge's old Homeland Security system. I am not, trying to equate in any way our homeland security with the choosing of an experimental design. I'm just borrowing his colors. But for the resolution 3 designs, there is a benefit for Plackett-Burman designs a little bit over the 2-level 2 to the k minus p fractional factorial designs. So that's why I've got orange rather than red there. And for resolution 4, which you can actually get by folding over the resolution 3 designs, that's where you just run the second set of experiments, where instead of the low, it's a high, and the high, it's a low for each of the experimental runs. You can get that. And of course, resolution 5 down there in green is the best. So as you go down, it's going to cost more experiments, but you get more resolution. So you try and pick a particular place to go. One example I won't talk about because I don't have the data, but it relates to the example I'm going to start talking about in the next chart, is within DuPont, we had in particular a real marketing DOE with many factors. Actually, there's 22 of them that are shown on this chart. The experiment was done with a 24-run Plackett-Burman design, and I'll show you a 20-run Plackett-Burman example here in a minute, but the 24 runs, actually, we went ahead and folded that over, which means if the first experiment was run at the low, low, high, 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 etc., another experiment in the folder was high, high, low, 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 was the folded over idea here. So they actually ran this experiment over 40 experimental runs with 48 different customers and in a certain region for a certain business. Of the 22 experimental factors that they were going to look at, a couple of them kind of fell out. So if you look on the x-axis, there was a dummy 1 and dummy 2 that didn't quite go. But we looked at 20 factors, and at the end of the day, this single chart, which shows 3 at the left that really were beneficial to increasing sales, and 1 over to the right that was really not beneficial. In fact, it hurt the sales. It says telemarketing. I wonder if they were calling it dinner. Any event, the ability of trying to see these 20 factors and what are the most important ones. This was a very powerful experiment that led to improved sales in the region of DuPont. So one more published example, and it's my first of the 4 examples I promised you, is the one that is published and we'll talk in some detail about. And it comes from the book Testing 1, 2, 3, Experimental Design with Applications in Marketing and Service Operations. A couple of authors there. And Hannes Ladolter is, in fact, an ex-George Bach student. And his example here, he lists 19 different factors, from the envelope teaser for factor A, return address for factor B, all the way down to the interest rate for factor S. These are 19 factors associated with mailing out something. And they got 2 different levels of each of those factors. The experimental runs that were run is a 20-run Plackett-Burman design, so the 2 levels are noted by a minus and a plus for each of these 19 factors, and those are the 20 runs, and the response was a percent positive response to the mailer. So they actually took each of these 20 combinations and mailed each to 500 customers, or 5,000, I should say. So do the math. This was 100,000 piece mail out, 5,000 each going to each of the 20 combinations here. And you can see on the right of the chart what the results were in terms of response rate, anywhere from less than 1% to close to 3% response. Just anything that improves response even a little bit is going to be very beneficial in this marketing application. When you take these 20 experimental data points and try to sort out the 19 factors, you've got the 19 factors and their factor effects here, and then of course the overall constant term, the average of all the response rate. You have used your entire data set up to understand the factors. So a couple of technical questions occur here. One is, well, which of these effects are real? And I've kind of hinted at the 5 that are shown here in white are the biggest 5 effects and are probably the real ones. But we can also put these on a Pareto chart, as well as looking at the effects on their actual benefits on the previous chart. And we can see there's one big spike, the interest rate there, and then second spike with the sticker, and then we've got the second buck slip, the copy message are both kind of about the same size, third spike, letter heading next, and then they keep going down there. So which of these are real? There's a number of ways to actually decide how to do that. You can just use the Pareto principle, look at the Pareto chart and decide, well, where would I cut off this as the most important ones to address? Actually, the authors went ahead and used a two proportions test. Remember that there were 5,000 mailings for each of these 20 conditions. So there were 50,000 that were run at the low level of any given factor and 50,000 at the high level. And they did two proportions tests on what if there was a difference in the proportions. And indeed, those top 5 factors I highlighted on the previous chart are the 5 that came out as being significant. Since this is a saturated model, we could also use a lens method for kind of sorting out things. And there's a bunch of stepwise analysis and other model selection rules in there that I won't talk about. Many people decide what on actually cutting off, what are the top ones that I really need to look at. So any event, those 5 seem to be the most meaningful ones. So the only other technical question I want to come back to is the second order effects. And here's an interesting thing about the Plackett-Burman designs. They do have some confounding of the main effect with interactions, but it's not as severe or all-encompassing as you would see in a 2 to the k minus p factorial design where it's a power of 2, okay? So one of the things that makes that nice is if we don't saturate our model, the error term that we use to decide what is and isn't statistically significant includes kind of these broken up small interactions, and so they just kind of increase the noise, and it's a good way to still figure out what the important effects are from that noise. And there is a way, and this is shown in the next few charts, teasing out significant interactions among the top Pareto factors. And that gets into these correlations that are between the main effects of the 19 factors, and for each factor, you could have as many as 171 different two-factor interactions affecting that main effect. The good news is that there's no correlations among the 18 interactions involving that factor, meaning that if I'm looking at factor effect A, its interaction with B, C, there's no correlation, perfectly uncorrelated. And most of the correlations that are around 144 of them actually are really small, just plus or minus 0.2. But there are a few correlations, even in the Plackett-Burman 20-run design, that the factor effect and the two-factor interaction that has a large 0.6 plus or minus correlation. And those are the ones that the authors kind of note when they go through their analysis and say, hey, look, we had 5 top factors, but let's look at the top 3 factors, S, G, and R, that came from the Pareto. And if you look at those top 3 factors, it's kind of interesting to note that there's a strong correlation between factor R and the SG interaction. That's one of the 0.06 correlations. And in fact, when you run the model on top there, you'll see that actually the SG interaction is important, but the R main effect, which was one of the top 5 spikes, isn't. So really, they're concluding, and I think properly so, that most likely what we're seeing is an interaction between S and G rather than the main effect of factor R in this experiment. And that's what the middle says there. And they bring back in at the bottom the 4th and 5th spike, I and J. So their final model, if you put on blinders, it might be SGRIJ as the top 5 factors. But because noting some of the correlation structure here, they felt S, G, I, and J were 4 important factors, and the SG interaction was the 5th thing to put in. So that's good. Any event, in applying the results, you pick they pick the right few factors and you send them to their preferred settings, or if you've got the trivial many, the ones that weren't important, either set them to their cost-effective settings. In other words, if something isn't beneficial, don't spend any money doing it, or you can use the preponderance of evidence settings. Even things not significant, and you might have hints from the factor effects plot of what might be important. And there's other things you can do about interactions, the fold over like I mentioned before, or just do a full factorial for the vital few x's. But the authors actually what they did, just to kind of close the loop on this, and that's an important part of all this, that usually these experiments aren't one-shot experiments and it's a sequence and you're learning. They took the top factor and combined it with 3 new factors and did a full factorial experiment here and got the ultimate results from this follow-up experiment with just 4 factors, seeing there were 4 important factors and 2 important interactions that came out of this particular second experiment. So that was the first experiment with the marketing using a Plackett-Burman design. I'm going to move now to example number 2, which is the heat sealer experiment. It comes from Wayne Taylor's Optimization and Variation Reduction and Quality book. He had a heat sealer which seals the top of plastic bags containing either supplies or potato chips. And there's 6 factors, and there's their current settings listed on this chart of what's there. But we wanted to see are those the best settings? Is there something that can give us a better target, but also reduce variation as well? So he actually studied 8 factors. Factors 7 and 8, as noted by notes A and B on this chart, were a couple of environmental factors he added. And he varied these 8 factors through the 2 levels that are shown there. And he ran the experiment shown on this next chart. There's the 8 factors and their various levels. Now, this is a 2 to the 8 minus 4 experiment, meaning there's 8 factors in it, but there's only 16 runs, 2 to the 4. So that's the shorthand. 2 to the 8 minus 4 says it's that fraction of the full 2 to the 8th experiments we could have run. And then in addition, he ran a center point at the beginning and at the end of the experiment. So that's why you have a total of 18 experiments. And at the end of the day, if you look at the complete analysis of those 18 experimental runs, you can see, and here's the Pareto again, the most important effect is the AB interaction. And the second most important effect is AA, which is A squared. But you got to be careful with these 2 to the K minus P experiments, especially if they're in the fractions, because the interactions, unlike the Plackett-Burman designs that are not a power of 2, these designs that are a power of 2, the interactions will land directly on top of main effects or on top of other interactions. They're fully confounded. So what I've shown in red on this diagram is that the AB interaction here could possibly also be the CH interaction or the DF interaction or the EG interaction, or perhaps several of them. And the A squared could actually be any one of the 8 factors squared terms. So that's what the center point check allows us to do in these designs, comparing the 2 center points to the average of the 16 factorial points. And then the Pareto goes down there. B, A, C, and D look like to be the 4 most important factors. So most important factors I've listed here in red on this chart. Here's the more detailed string of what interactions are confounded with what other interactions. But we've identified the 4 most important variables, A, B, C, and D. We want to resolve the curvature and the center point check at the bottom of this chart. We also want to resolve that interaction string that was labeled AB. And we can do that with an augmentation of the original design. So we can actually just add some extra experiments. You could do something as simple as just using what's called axial points for augmentation. I'll use that later. They did something slightly different. They actually were using E-chip here when they were running this experiment. They did a computer-aided augmentation of this design that led them to this final answer, that A squared is the squared term that's important. B squared is actually also important there. You can see it down there a little bit. And AB was indeed the interaction of importance, and they were able to get the results they need with this full understanding of these 4 factors. And for those that love to look at output rather than pictures, here's all the output from the full response surface of that 4 factors and their squared terms and their interaction terms. The experimental runs can estimate all the ones that are listed, but we can drop out the ones in red as being unimportant and come up with a smaller model if we want. Okay, that was example number 2. I now want to move from the screening world to the optimization world, if you will. Okay, both of the examples I previously showed you started with screening experiments and actually did some follow-up experiments afterwards. But I remember one of my ex-DuPont and ex-George Box student, Dave Bacon, once wrote an article back when on making the most of a one-shot experiment. There may be situations where you just got a smallish, maybe not small, but number of factors, and you just got one shot to experiment, and you want to make the most of it. And response surface designs are a very good way to do that. The purpose of this chart I'm showing you right now, which is very busy, and I could spend a whole webinar just on going through all the principles of design experiments that are on this chart. But let me draw your attention to the degrees of freedom row, because basically if you think about designed experiments, you're trying to, with an efficiently small number of runs, n, you want to estimate the number of parameters in some model you're considering, p. So p is the number of parameters in the model. You don't want to, if you got 1x and you're fitting a straight line, you can do that with 2 data points, but you don't want to just run a 2 data point experiment. You'd like to have some extra experimentation for lack of fit. So the L in the next circle is the number of additional treatments beyond the minimum to check for lack of fit of your model. And then if you can put it in your budget, a little bit of pure replication. We saw a hint of that in the second example with the 2 center point runs, but you might add a little bit more here to come up with a high quality model is what's happening. So n equals p plus l plus r is kind of the equation that we'll be looking at. The p for a quadratic polynomial model, I've got models with 1, 2, and 3 factors here. The third model here, you can see y equals b naught plus 3 terms involving x's, 3 more terms involving the interactions between 2 x's, and 3 more terms involving the squared terms for the x's. So that there are p equals 10 coefficients that we want to collect data to estimate those so we can get a full quadratic polynomial model describing our situation. And we'll come back to in examples 3 and 4, those questions in red on the bottom. Well, Box and Wilson back in 51, Box in 157, they developed these class of designs, response surface designs called central composite designs. They start out with the data points on the cube, the 8 corners for 3 factors, if you will. And then what they add are these axial points, which for this drawing, I have as face-centered, meaning they're also at plus or minus 1. So there's 6 of those, and then there's a center point that we typically will do our replication at. So there's 15 distinct conditions shown here on this chart in this central composite design. Those 15 conditions give us 5 more. L equals 5 more than the minimum number 10 we need to estimate the quadratic response surface. So that's one class of cataloged response surface designs. The other class is called the Box-Benken designs. They were developed in 1960. Don Benken, who's pictured there on the left with George Box on the right, they were in the right-hand corner of a Gordon Research Conference picture, so I snipped that out. It's the only time, unfortunately, I ever did meet Don. This was well after he had been with DuPont, and his long career was with American Cyanamid. But in any event, they developed in 1960 the Box-Benken designs, and for 3 factors, there are these 12 edges of the cube plus the center point. So there's 13 conditions, which are 3 more than the minimum. And the whole idea is you don't have to run the 3 times 3 times 3, 27 combinations. You can either run this half or the other half to get the response surface you need, and that's efficient experimentation. Okay. Now, sometimes you can't run the catalog designs, and the 2 examples I'll mention in a moment will give you issues where it's tough. So what you're able to do using the good design principles, but letting the computer try to come up with quote unquote optimal designs. I like to call them custom designs. Basically, if you identify your factors and the constraints and other things that are causing issues in using a catalog design, figure the model you want to fit, which gives you P, the number of model parameters, and then you kind of set your desired number of runs, how many experiments you want to run. And Bob Wheeler, again, the E-chip inventor and ex-DuPonter, his rule of thumb was 5 plus 5 is a good rule. So the number of experiments is number of parameters plus 10, if you will. Generate your optimal design, review the diagnostics of that design before running it, and you're off and going. When I talk about optimal design, and don't have time to really delve into it, there's a lot of different optimality criteria out there. Some people just like to call it alphabetic optimality. But the two that are most prevalent out there are de-optimal designs, minimizing the variance of the coefficients. That's good for an estimation, if you will, of effects and what's significant. And there's I-optimal designs that could have maybe preferred for predictive purposes. And these examples, both are good, and we'll use de-optimal approach in these two examples coming up. So there's a whole literature out there on that criteria, but software makes it available for you to do it. But when would you need to do it? When do you need to get away from the cataloged experiments? Well, this example 3 is one such example. It's something I did with Avellino Lima DuPont application that we wrote up for a Minitab case study. We were looking at new stabilizers. We were hoping to use them at the lowest amount, and we were trying to qualify new vendors. So there were goals and importance of this experiment. And for the experiment, we had 5 factors. We had an amount of reinforcement, an amount of colorant, and an amount of stabilizer. Those were continuous variables, which we coded -1, 0, and 1 here. There were 2 categorical factors. There were 3 different vendors we were considering. We'll call them 1, 2, and 3. And there were 3 different types of stabilizer that we also called 1, 2, and 3. So those are categorical factors. And I've seen people mistakenly say, well, geez, isn't that the box Benken design, for example, have 3 levels? Why can't I just use that? Well, categorical factors, a little bit different animal in that regard, and you need to kind of consider things a little differently. But however, the thing we're not going to do is run 3 times 3 times 3 times 3 times 3, 243 possible treatment combinations. So what we're going to do is come up with a custom design to address this problem. The other nice thing about these last 2 examples are they actually are a large number of responses we're looking at, okay? There's actually 19 responses in this experiment, and we want to make sure that they're all behaving well with respect to whatever we decide comes out as a result of our 5 factors affecting these 19 responses. Now, here's a scary chart. I don't expect you to check this out, but if I had C factors that were continuous and D factors that were categorical, and each of those D factors had category, a KI level. So maybe categorical factor, maybe it was 4 vendors and 6 different machines or something like that. So this is a very generic chart for an experiment with categorical and continuous factors. All it does is says, well, how do I calculate P, the number of parameters I'm going to have to estimate? That's at the bottom, and there's that ugly formula. I'm not going to stay on that chart anymore, but for the specific case of where we had 3 continuous factors and 2 categorical factors at 3 levels each for the example I'm going through, when you add it all up, there are 30 parameters that you have to estimate in the full quadratic response surface. So you've got those 30, and I decided to add 6 rather than 5. The rule of thumb is 5 extra from Bob Wheeler, but 30 plus 6 gave a nice, 36. It multiplies by, 3 and 6 and 4 and all that good stuff. So I did that, and then I did add 5 replicates. So the full experiment is 30 plus 6 plus 5, 41 experimental runs. And we looked at 19 responses here, and there's 2 ways that I show this graphically. There's the, this is not the graphical, this is the tabular version, the stoplight chart, if you will. And so on the right-hand side, you can see what's going on with respect to the 5 factors. The really important factors are in orange and red. But by and large, the different vendors, there's not very much importance with them being different, and stabilizer types, same type of thing as well. All models on the left-hand side of this chart, they're really good. If you look at R-squared adjusteds, all but 3 of them had really nice R-squared adjusteds. If you look at lack of fit, which we can test because we have both experimental error, pure error from the replicates, and lack of fit there's a few that didn't. There's only one model that was a bad fit, but also had a bad lack of fit, and that's YB3. But by and large, good model fits happening after all of these. That's the tabular chart, but the graphical chart, this is called a response optimizer in Minitab, and that's called a prediction profiler in Jump's version of it. And truthfully, Jump was first to the gate. Actually, a predecessor of Jump, Brad Jones, was probably the first to actually think of this type of graphical display well before he joined Jump. But it's really a really nice way to look at. It's a dashboard basically, where each column is each of the factors in your experiment, and I had 5 columns, 5 factors, and each row is one of the responses. And this thing actually, I can toggle it all the way down to see all 19 responses. I'm just showing you YA 1, 2, 3 and YB 1, 2, 3 here. And if you set the conditions in red for the 5 X's on the top, you get the predictions in blue on the left-hand side for each of the Y's. And of course, the S and V are categorical variables, and that's why you just see 3 dots rather than curves. And you can plug and play with this thing. And hang on a second, I'm sorry about that. So it's a very good graphical display that you can look at to kind of understand things. And long story short, we had from this experiment, we were able to show that there's not much difference among the 3 stabilizer types, so we can use the new stabilizer we're considering. We can reduce the stabilizer amounts to their lowest levels, and there was minimal statistical differences among the 3 vendors who qualified the new vendor. So there was a marked importance to this. This was actually a 6 Sigma project within DuPont, and it saved a bunch of dollars. So I'll just leave it there and move on to example 4, also from DuPont. So in example 4, we have a different situation. We have 8 components, but it's a mixture experiment we're going to deal with now. Our TiO2 business was trying to optimize the efficiency of using in conjunction with functional extenders, and the application was in agricultural coatings. So we had 8 components. They got to add up to 100% because you're mixing them together, and each component had lower and upper bound constraints, and you'll see in the next few charts how that causes challenges in figuring out what a DOE is. But long story short, this is like the 1-page summary of this case study. We ran 47 experiments because we needed 36 runs to estimate all the effects in our quadratic model, which is kind of a special form, as you'll see in a moment. And then we added 5 extra for lack of fit and 6 extra replicates, and that gave us the 47. We had 10 responses, so this one has 47 runs and 10 responses with 8 components, just like the previous one had 41 runs with 5 X's and 19 responses. So big experiments, and then we had good fitting models here. So how does mixtures are slightly different and leads to the use of the computer to come up with designs? Basically, the first part is if we were to write out our, and I'll just look at 2 components here, 2-component quadratic response surfaces there at the top, but that A0 term is multiplied by 1. And of course, 1 I can rewrite as x1 plus x2 if the 2 x's are the mixture, gin and vermouth if you want, for example. But if you can just replace 1 by x1 and x2, you can replace x2 1 squared by x1 and x1 x2, and you replace x2 squared by x2 and x1 x2. So the top equation can actually be rewritten as a very simple 3-factor quadratic mixture: b1 x1 plus b2 x2 plus b1 x1 x2. Okay, and in regular response surfaces where those x's are continuous, we call x1 x2 an interaction. It's best called here a nonlinear blending term because look at this chart. If I were talking about the cost of a blend, that straight line b1 x1 plus b2 x2 would be the right answer. If this if component 1 costs b1 dollars a gallon and component 2 costs b2 dollars a gallon, then the mixture of the 2 is going to be on that straight line. But the other aspects, the taste, the aesthetics, the other properties can have some nonlinear effects associated with it. You're probably blending these two together to find something good somewhere in the middle. And that B12 term kind of measures the curvature. Now, with the 8 factors, we got a lot of terms, and I mentioned stepwise regression here because I'm just jumping ahead a couple charts. Here are the 8 components in our 36-term model, okay? And this chart looks kind of cute, but every line is a possible nonlinear blending term, and there's 28 of them, plus the 8 the linear terms. So that's our 36-term model that we have to fit here. And notice there's lower and upper bound constraints on these x's. And so with a lower bound and an upper bound, just to use a 3 component example here, notice we're drawing these on a ternary diagram. So each of the 3 corners of this triangle is all x1, all x2, and all x3. And if we put lower bounds only on them, we'll end up with a smaller triangle that's kind of in the middle. But if we also put upper bounds, we come up with kind of a funny experimental region that's shaded there. And of course, that gets even more crazy when we get into 8 factors. So that's where you need to use the computer to come up with good candidate experiments, and then from those candidates, choose the best ones to run. And that's what we did, and that's what we fit the 10 responses here, the 10 responses, and we fit these models to the data. And I did mention stepwise regression. It is true that the DOE you generate can estimate all the nonlinear blending terms as well as all the 8 linear blending components. The 36 terms of the model can be estimated all from the data, but a lot of them aren't that important. And if you leave all those in, it can kind of really sacrifice your predictability, if you will. So we did use stepwise regression to remove those unimportant nonlinear blending terms to come up with the models that you see summarized here. And you can see all these, all but one of these have, or at least 90% for R-squared adjusted. And R-squared predicted, which is a good first blush at how well you're going to predict, given no extra data to predict from. Basically, what R-squared predicted does is, hey, let's take our data set, remove one of the data points, fit the model without that data point in, and then see how it predicts the data point we left out. And we do that for every data point. So it's kind of like R-squared adjusted looks at all the data. R-squared predicted gives you a little bit more of a comfort feel that your model is going to be good predictability. And we're getting good comfort in almost all cases here with respect to how well the model fit. We didn't just stop here in this study. We actually went out and tried to test with some extra confirmation runs, and they worked out wonderfully. Here again, just to show you one more time, is the 8 components or the 8 columns there. And then over here, you've got the various responses. I can only fit 6 of them on the diagram here, but there are 10 of them. So you've got your response optimizer you can play around with. And of course, this time when you change one of these components, the other components have to change too, because you got to keep the 100%. But that's all built into the software, and it works out really, really well. So this last case study that I mentioned was actually published in Coatings Tech back in 2014, a couple of co-authors and myself, and we've replicated this successfully in many other mixture DOEs as well. So I'll just leave it at that. So I have walked through these charts and left hopefully a small amount of time for questions and comments. But to wrap up, I'll say it's a wonderful life. For those of you who know that movie with George Bailey in it, well, I'm Steve Bailey, but I've been blessed in the sense that I spent my 1970s at the University of Wisconsin, go Badgers, and that's where I first met George Box and his colleagues, and had many fellow students there that just had a great time there, and just a really enlightening start to my career. The next 36 years of which was with DuPont's Applied Statistics Group. More amazing colleagues and all, and I still work today for DuPont as an external consultant as well. So So hopefully George, who would have turned 100 in this Friday, he's done pioneering work in so many areas, but especially design analysis experiments. And I mentioned how that had an impact in DuPont's strategy of experimentation that we've been doing for over 50 years. Hopefully you saw in the two screening DOE examples I presented that, two-level fractional factorial experiments are a good first step in the strategy experimentation approach. And I hope you also got an appreciation for the optimization DOE examples, that there can be situations that go beyond the catalog designs, and they can be handled very nicely by computer-generated designs and analyses for optimization. So with that, I'll stop and I guess ask Steve if there's questions, discussion.
Okay, well, thank you, Steve. That was quite a good education in experimental design. I know myself, I was fortunate many years ago to go to the University of Wisconsin for a presentation by Conrad and Dr. Box on experimental design, and had the pleasure of being invited to his house. So that was a special moment for me. So if you have questions, let's see what I have. Okay. Here's a question. So Box often recommended normal plots of effects after Cuthbert Daniel to analysis of two-level designs, but you didn't mention this method in your list of analysis methods. I just wondered why not.
I actually did. It was kind of hidden. If you think of normal probability plots, you look at them and you try to see which of the effects are falling outside of what could be normal variation of those effects. And when I mentioned in the first example, I mentioned length, who used, he actually starts with normal probability plots, but then says, hey, look, if we take the ones that are in the middle and assume they're noise, how can we come up with an algorithm to kind of decide or declare which ones are important? So he kind of put an algorithmic top to normal probability plots. But I'm very much a big fan of normal probability plots as a graphical tool to kind of figure out what's important.
Okay, thank you. If anybody else has a question, go ahead and send it in the questions box. Of course, this webinar, like all the different webinars provided by the Statistics Division, are available on our YouTube channel. If you go to youtube.com and search for ASQ Stats Division, you'll find that link and be able to see this webinar, probably posted within the week, and previous ones that we've had on other types of topics. As I wait for another question, will the slides be available?
Yes, I'd be glad to share a PDF version of every slide. Yep. Okay.
So typically what we have been doing is posting these slides in our My ASQ location on the Statistics Division. And for those that are members of ASQ, step one is to join My ASQ, and that opens up a plethora of other communities besides the Statistics Division. But if you go there, you can download the slides. We do have another webinar scheduled in early November. It'll be on chi-square testing. It'll be a joint webinar with the Six Sigma Forum. So we have done 2 webinars with Six Sigma Forum. We did one earlier this month with Quality Management Division, and we're looking to do one with Lean Enterprise in early 2020. Any other questions?
And anyone too shy to ask a question publicly and wants to send me a question, there's my email address. Feel free to use that.
All right. And not seeing any other questions. Again, thank you, Steve, for the presentation, for reminding us about the contributions of George Box to our profession. I won't say go Badgers, but we appreciate all that you've done for the field of statistics and especially for ASQ.
I'll end up with a little anecdote. You mentioned even going to George's house when you visited, Steve, and he had something called the Beer and Statistics Symposium, he called it. It was at his house on Monday nights. There'd be a case of beer and a researcher with a problem. We just sit in his basement and talk about it. And believe it or not, at Wisconsin, you even got 1 credit for that if you did it over the semester. So that probably was my favorite course.
Yes, I remember his house having a big round area to be able to have those discussions. So if no other questions, then we will conclude the webinar now. And again, we look forward for your participation in future webinars, one in November, and of course in 2020, we'll have another set of webinars available, either posted or advertised on LinkedIn or at our My ASQ. With that, I thank you and concludes the webinar.
Thank you, everyone.